Welcome back to Math 365 PDE. It's great to see you. Shall we get right into it? So today's lecture, lesson, whatever, is on distributions. What are they? Why do you care about them? We'll try to do this with document camera. There we go. All right. And certainly, as you know, you can always ask questions as we go along. Feel free to interrupt me and we can keep on going. I've got it set up so that I'll sort of reveal the next line, but then we also have some blank paper that we can write more things on and do math and ed. So it's not exactly like a PowerPoint, right? We can stop and explain things. Yeah, we were speaking about function spaces before we started the recording, so we'll jump right in with a function space, right? So the idea being that you fix some domain in Rn, or for our examples, usually just R or R2, sometimes even R3. And a domain is a connected open set. Most often we're looking at bounded domains. And you look at C infinity compact support of omega. So these are all the functions defined on omega, such that all partial derivatives of all orders exist and are continuous, and such that the support of each function is compact. The support being the closure of the set of points in the domain such that the function is non-zero. Closure meaning take the set of points in the domain where the function is not zero and include the boundary of that set. That's the support of the function. And going through and reading Borthwick's arguments, it seems like he also wants the support of the compact support of the function to be a strict subset of omega. It's just a small technical detail, but anyway, the definition of C infinity compact is what I said it is. And Laurent Schwartz, when he was writing his papers, his books, he called this D. And I'm using a script D to denote that, but I don't always keep that consistent through my notes because sometimes I forget to do it. Fine. So this collection is a vector space. As we know, like we can add any two functions together, we can multiply by a scalar, it stays in the collection. More generally, given any vector space V, I'm going to define the dual space denoted by V star. Given any vector space V, the dual space is as follows. It's the collection of all functions from the given vector space to the real numbers that are linear. Functions from the vector space to R, we usually call them functionals. So the dual space of V is the collection of all linear functionals on V. In what sense is this dual? In what sense is this dual? Well, actually, let's take an example. So let's look at Rn from linear algebra. And yeah, okay, right. So I'll take my own advice. Can you think of so given Rn, can you think of an element that's in the dual space of Rn? Knowing what you know from linear algebra. What's a function that takes a vector as an input and gives a real number as an output? What do you think?
A dot product?
Yeah, you're totally right. So in fact, you can prove that every linear functional if V is equal to Rn, you can prove that every linear functional is a dot product with some vector. Yeah, so in fact, that's my next line. So typical elements of the dual space in this case are dot products with some fixed vector. And this is going to let you identify the dual space, in fact, with Rn. So like in some sense, Rn star is equal to Rn, but you have to identify the function that takes A and takes an input W and gives you the dot product. You have to identify that function with vector A. I'll probably say that next. Or actually, well, next I'll introduce some notation. We use the pairing FW in place of F of W. We use those interchangeably. So for an element of the dual space F, instead of writing F of W, I'll often write F paired with W. And you'll see why that notation is natural in just a moment. And so, yeah, here's my remark that I was saying. So this like little theorem. If the vector space is Rn, then then it's possible to identify the dual space with Rn itself. And so what does that little equal squiggle mean? It means that there is what we call a linear isomorphism. So it means there's a linear function between Rn and the dual space, Rn star. There's a linear function between them that is injective and bijective. So if you're also taking algebra, then there's a group isomorphism between the vector space and its dual. So I'm not going to tell you like the full proof, but the idea is to identify function f with the vector A, right? So your strategy is given a functional in the dual space, prove that it's equal to A dot product W. And then your function from the dual space to Rn is just going to be take F and send it to A. And then you need to do some work to prove that it's injective and bijective. It's not super hard, but that's sort of like for a different class. It's for an algebra class. And there's definitely lots of details to check. So that's just to give you some idea about what a dual space is and give you some context for like what it is for Rn. This works for any vector space. In fact, it works for vector space D of C infinity compact support. You can also consider the dual space. So can you think of an example of a element in the dual space? Can you think of an example of a function that takes C infinity with compact support as an input and gives you a real number as an output? What might such an element of the dual space look like? So instead of the dot product being linear that gives you ideas, what's the linear? Yeah.
An inner product?
An inner product, but which inner product?
The L2 inner product?
Yeah, that's right. Or integration. So if you have some L1 loc function on Rn, so some function that given any compact set, you can integrate over it. This lets you define an element in the dual space, just as you say, by taking that L2 inner product. And definitely it's going to be true that the product of an L1 loc function with a smooth, C infinity function with compact support, that's going to be integrable. And note we've got fixed domain omega. So in other words, every function f can be identified with an element of the dual space in the same way that every vector in Rn can be identified with an element of the dual space to the dot product. But the element of the dual space isn't literally f, it's the function given by like integrating against f. And actually I should fix my notation. I should say, I'm kind of switching notation. I should say, like, if u is an L1 log, then you may consider u to be a element of the dual space by the following pairing. So you'll see me use the same notation for the L1 log function and for the dual space element. And that's common, but just remember to keep it straight. But there are other elements in the dual space. It's not true that every element of the dual space is integration against a function. Here's an example. So the Dirac delta. What this properly is an element of the dual space of these C infinity functions in compact support. And here's its definition. That delta applied to psi is psi of 0. Oh, and by the way, you'll see D be called the space of test functions. And we're looking at its dual space. So I've given you two examples of elements in the dual space. One is integration against a function, and the other one cannot be represented as integration against a function, but it's still in the dual space. Okay. Yeah, and there's delta x, evaluation at x instead of evaluation at 0. So in some sense, there's nothing to delta. It's just the evaluation function, right? And it's certainly linear. Okay. Any questions or comments on any of that? All right, so I want to now define for you the space of distributions.
Hey, Ken, could you put that last sheet back up?
I mean, I can scan them and put them online too, if you prefer that.
That'd be super helpful.
So I want to define for you the space of distributions. It's not exactly the dual space. It's a subspace of the dual space. So it's what we call D prime instead of D star. So the space of distributions is the subspace, the vector subspace of the dual space given by linear functionals that are also continuous. Sometimes in advanced textbooks, you see this called the topological dual. So not just asking for linear functionals, but also continuous linear functionals. Let me say a little bit about what it means to be continuous in this context, but not too much. And so D prime, this is the space of distributions. It's a vector space. So subspace of the dual space. And I'll make a little note. If you're comparing this to vector space V equals Rn, it happens to be true that being linear is totally equivalent to being continuous. So if you were making this construction with D being Rn, you wouldn't need to add the distinction that it's continuous, because that would just be given to you by linear. More generally, for arbitrary vector space, like infinite dimensional arbitrary vector space, not just Rn. I'm not going to prove this to you, but it happens to be true that an element of an arbitrary vector space is continuous if and only if it's not just linear, but also bounded. It's to be a bounded operator. It's just sort of for your reference, but I'm not gonna, you take a class on functional analysis if you want to talk about this stuff in great detail and depth. In particular, so that was just a note for you, but in particular, what does it mean to be continuous? So like, what fact about continuity am I actually going to use? The fact that I can take limits of sequences and, bring the limit like inside of the function. It's the characterization of continuity that you use in calculus, and it's the consequence of continuity that I want to use here. So in particular, if you take a sequence of functions inside D, take a sequence of test functions that converge to psi, and yeah, you can ask me in what sense do they converge. So there is, I guess just for Bill, there is a topology on D, it's a Fréchet topology, and convergence in that topology means that on every compact subset, this converges uniformly and all of its derivatives of all orders also converge uniformly. But yeah, if you haven't had topology yet, then convergence in D means that this and all its partial derivatives also converge. But you can, that's not going to be a huge issue. So if you've got a sequence of test functions that converge to a limit, then it'll also be true that take that distribution, apply it to the test function. Now you have a sequence of real numbers. And this will be equal to u applied to the limit. Correct that little mistake there. So the limit of u applied to psi k is equal to u applied to the limit of psi k. That's what you get from asking that all your functionals are not just linear, but continuous. Okay. So for example, this is just examples of distributions, and get the autofocus going a little bit better. Okay. So the delta from before, that was an example of element of the dual space, but it's also continuous. It's also a distribution. If you take any f in L1 loc and consider it to be an element of the dual space through integration, this will define a continuous element of the dual space and will therefore be a distribution. Oh yeah. So you'll have to, if you think there's a joke here, forgive me for it. If you don't think there's a joke here, don't worry about it. It's possible to multiply a distribution by a function. So they're not just a vector space over scalar, like there's a vector space over functions. So given u in the space of distributions and given a test function, you can multiply them together. So f times u is going to be a distribution. In what sense? Here's the definition. So f times u, what distribution is that? Well, if you apply it to a test function, it's going to be u applied to f times psi. So this really is a definition. So for example, take delta x I create a new distribution f times delta x. So what's its definition? It's just going to be delta x applied to f times psi. So the distribution given by multiplying the evaluation function by f is nothing but evaluating at the point f, times at the point psi. So it's actually quite natural. However, it does not make sense to multiply two distributions together in the same way that it doesn't make sense to multiply two vectors together in a general vector space.
Is F Hermitian?
F is an element of D. F is a smooth function with compact support. Nothing is Hermitian here because we're not talking about complex numbers.
Oh, okay.
Do we have a formal definition of what a distribution is?
Yeah, we've done that. So a distribution is the set of all elements in the dual space that are continuous, where D is the set of test functions. So D prime, that's your space of distributions.
So if it's in D prime, it is a distribution?
That's the definition of being a distribution, yes.
Okay.
With D being the space of test functions. So you fix a domain omega, then you look at the space of test functions, then you look at the dual space, then in that dual space, look at those elements that are continuous. That's the space of distributions. And there's other ways to characterize it, like in other textbooks or whatever, but this way of characterizing it is pretty good, I think. And so, yeah, there were two examples, and there I've shown how to multiply a distribution by a function. And one more technical thing I want to point out is if I have a sequence of distributions, what does it mean for that sequence of distributions to converge to a limit? So you know what it means for a sequence of numbers to converge. Roughly speaking, those numbers should get closer and closer and closer to the limit in absolute value as k goes to infinity. What does it mean for a sequence of distributions to converge to a limit? What it means is that for every test function, if I apply each member of the distribution to that test function in turn, giving me now a sequence of real numbers, then that sequence of real numbers will limit to the real number given by distribution U applied to that test function. So if this sequence of real numbers converges for every single test function, no matter what, then I say that the UK converge to U in the sense of distributions. So that's what it means for a distribution to converge to a limit. And I'll give you an example, of course, but are there any questions on that definition? Okay. So let's do an example. It's a little bit involved, not too involved, bear with me. So for example, let's consider the function f of x equals 1 over 2 pi times e to the minus length of x over 2. So this is a function from R2 to R. And of course, that length of x means square root of x1 squared plus x2 squared. And I'll note to you that f is a distribution. You can think of f as a distribution with the following formula, that f applied to psi is just the L2 inner product. And I'll also note that I've chosen the scaling. I did you dirty a little bit, like, oh, and this is like R2 instead of Rn. I said note that this integral is equal to 1. It's actually non-trivial to to prove that. It's non-trivial, but it's classic to prove that. But basically I'm just telling you that this integral is equal to 1. This kind of looks similar to a normal distribution, if you're familiar with that from statistics. Okay. Now, let's kick it up a notch. So define sequence Fn as follows. This is basically a change of variable. So I'm scaling the function, I'm scaling the domain. I'm doing like a horizontal shrink by a factor of 1 over n, if you like. So focusing in on 0. And then I'm scaling the values by n squared. I'm doing this so that the integral is going to stay equal to 1, right? If you integrate this and then change a variable like y equals x over n, then the n squared will cancel, and the integral will still be equal to 1. Now, I claim to you that f sub n converges to Dirac delta in the distributional sense. So Fn is a distribution in the sense of applied to test function psi, you're just integrating against it. I'll show you that these things converge without working out every last detail. So I need to show you that Fn psi, as n goes to infinity, gets closer and closer and closer to delta psi. That is to say, it gets closer and closer and closer to psi of 0. So what's happening? Just write down the definition of f sub n applied to psi. There it is. You do that change of variable I was talking about, say like y equals x over n, then changing to the new variables, your area element gets multiplied by 1 over n squared, which cancels out this n squared factor that's given to you. Nx becomes x and psi becomes x over n. So like you could do the change of variable and then relabel the variables x after you're done, because for definite integral, it doesn't matter. So I'll let you check the details on that. So now you're seeing something that, like, what happens as n goes to infinity? That's what you're kind of asking yourself. Well, I'm going to note also that psi of 0 is equal to integral of f of x times psi of 0 dA due to integral R2 f dA equals 1. So I picked that condition for a reason. Just bring in the constant there. So multiply this, on both sides by psi of 0. And so, of course, psi of 0 is going to be delta applied to psi. So I want to look at the difference of f sub n psi with, that's ghost, sorry about that. The cat getting in the camera. So I want to look at the difference between Fn applied to psi and psi of 0 and show that that difference is very small. And that's what I'm doing now.
Wait, Ken, could you explain the change of variable step just a little bit more?
So, I mean, you just take y equals x over n. And what's going to be, I don't know. I mean, just work out the change of variable, right? So the determinant of, I mean, this is linear function, so it's equal to its own derivative. The determinant's going to be 1 over n squared. And then you'll be,
You might want y equals nx if you're going to go from left to right.
oh yeah, okay, right. Yeah, sorry about that.
Then you'd have an intermediate step with whatever y is in place of what ends up being x on the
Right.
right side.
So this is going to become f of y. And then psi of y over n. And like if this was like dx1, dx2, then dy1, dy2 is like n squared dx1, dx2. Yeah. Thank you for the comment, actually. Right. In my mind, without thinking too hard, I got the statement switched, but that's what you want to see. But it's also quite standard. Okay. And so we go here and we want to look at the difference between Fn psi minus delta psi. And just plugging in these two things, it's going to be the absolute value of the integral, which is less than or equal to the integral of the absolute values, which is f of x times psi of x over n minus psi of 0. And this is the part where I will ask you to just believe me that look, for a smooth function psi and for a fixed value of x, psi of x over n minus psi of 0, that's going to 0. So this expression is going to 0. You need to do a little more work to prove it formally. That proof is in Borthwick if you want to check out the details. And it is pretty well written. So this tells me that this sequence of spikes, right? Like it's not a bad exercise to go plot some of these FNs. This tells me that this sequence of functions that get more and more spiky limits to Dirac delta. And this is why engineers say that Dirac delta is a function with an infinite spike at the origin, isn't it? Because in the distributional sense, Dirac delta is a limit of functions that rapidly decrease to 0 and all have integral equal to 1, and you know the y values tend to infinity as you take the limit. So the thing that physicists and engineers are misspeaking when they're talking is they're misspeaking by saying that Dirac delta is literally equal to function with infinite spike. So what they mean is just that in the distributional sense, you interpret this function Fn as a distribution, you take its limit, then that limit will be Dirac delta. So it's just what we've done. Oh, and you may recall this solution to the heat equation. I think I wrote it down maybe even on the first day of class. So the solution to the heat equation on R2. take the limit as t goes to 0. And this will approach Dirac delta in the sense of distributions through the same argument. You can see it's a function of a very similar character. And you can see this minus n over 2. That's because it's a solution to heat equation in Rn, like upper half plane of Rn. So this n is fixed, and you're letting t goes to 0, and you'll see this rapidly decreasing function, the spikes heading to infinity. Same argument. It'll work out for you. So give that a try.
Do you need a minus sign on the absolute value of x?
Oh, yeah.
I think Borthwick had that problem too.
Right. Minus, certainly minus.
Is the denominator of the exponent just 4t?
Due to like parabolic scaling, right? One t derivative and two x derivatives. Okay. So I've told you a lot of things, but we need to learn about, so here's why you care about it. So here's the thing. We started with functions that are differentiable. They give us classical solutions to PDE, but there's many more solutions to PDE, not just classical solutions. So that leads you to the concept of weak derivatives. Weak derivatives still are not good enough. You take a function with a jump discontinuity. This function has no weak derivative. So that's no good. So you seek a concept that can be, in a sense, differentiated infinitely many times, no matter what. And distributions are those things. Of course, you can't literally differentiate a distribution in the pointwise sense, but there is a generalization of derivative that applies to distributions that has the property that you can differentiate a distribution as many times as you want. So every distribution is infinitely differentiable in this sense. It doesn't have the problem that weak derivatives do. That's why we like distributions. So I want to tell you how to define a distributional derivative, and it's actually quite natural. It makes a lot of sense. If u is a distribution, then define the partial derivative of u in the ith coordinate direction. So like working on Rn, perhaps. So what's the distributional derivative in the ith direction? Well, for weak derivatives, I would just say integrate by parts, but there are no integrals here. Like there might be an integral, there might not. What this pairing means is simply, well, this is a definition. So I'm defining the left-hand side in terms of the right-hand side. And what the pairing means is simply apply the distribution to the derivative of psi in the direction of xi, and then include a negative sign. And this is brilliant because psi is infinitely differentiable. So you'll always be able to put as many derivatives as you want on the other side. And in the special case that the pairing is given by integration, this does reduce to the integration by parts formula, which is great. So it's a strict generalization of weak differentiation, which itself is a strict generalization of the usual differentiation. So I can't stress enough how awesome this is in that it generalizes these concepts so well, but it's also so dang simple to write down, you know. Once you've got everything defined, which is the hard part, there's nothing to it. So yeah, like as a note, if U happens to be an L1 loc function, and if that pairing happens to be integration, then du dxi will be the weak derivative of U, supposing that du dxi also happens to be an L1 loc function. And what's the official definition of distributional differentiation? So not just in one coordinate direction. We spent some time last time talking about the definition of d alpha of U, where alpha is a coordinate. So alpha is like an element of Rn. And so here's the official definition, like however many partials you take, multiply by -1 that many times, and just bring all those partials to the other side of the equation. I mean, so when you look at this, you think like, what's going on? But you have to remember, it's just this. But however many partials in whatever coordinate directions you've got, just switch them all over. And every time you switch it, add a negative sign. And then it reduces to this big formula. Yeah, examples. So what's the derivative of Dirac delta, right? That's what I'm going to tell you. So Dirac delta at the point A, so evaluation at the point A, what's the derivative in the distributional sense of that? So every distribution has a derivative guaranteed. What is that derivative? And let's take, for example, n is equal to 2, so we're on the plane. What's the derivative of Dirac delta in the y direction? I just bring it over with a negative sign and apply the evaluation function to this, and what I get is the negative of d psi dy at the point A. This makes perfect sense. So the derivative of the function that evaluates you at a point is the function that evaluates you at the corresponding derivative. So like it makes sense that that would be the derivative of the distribution. So the derivative of the evaluation functional is the functional that evaluates you at the derivative. It's a little bit of a tongue twister, but makes sense. What else? Yeah. Let's get to this. Function that had no weak derivative, but it will have a distributional derivative. So instead of writing out the formulas, I mean, you can write out these formulas pretty easy. So this is just w is the function that's going to be equal to -x when x is less than 0, and equal to x plus 1 when x is bigger than 0. And you can see its piecewise derivative written thusly, just -1 for less than 0 and +1 for bigger than 0. And we saw last time that h is not the weak derivative of w. W has no weak derivative because the boundary terms for integration by parts screw you up. But this does have a distributional derivative. It's a distribution. It has a distributional derivative. Let us figure out what it is. So we need to do the work. So by definition, w prime applied to psi will be equal to the negative of w applied to psi prime. Since w is L1 loc function, as a distribution, applying it to psi prime is integration. So what I've got here on the left-hand side of the page is sort of in some sense the answer. That's that's the derivative of w as a distribution, but I need to rewrite it in terms of just psi so I can get a good formula for it. And using integration by parts, I can see that this is equal to psi of 0 plus h times psi. I'll let you work that out. And so the distribution of W prime is nothing but Dirac delta plus H. That is to say, W prime applied to psi will give you psi of 0 plus integral of H times psi. So any questions or comments on that? So I didn't do every last detail, but I trust you can go from here to here, you're breaking up the domain from negative infinity to 0 and then 0 to positive infinity, using the fact that psi is C infinity compact support. We'll give you, yeah.
A really dumb question, but I thought there was no way to integrate.
No way to integrate?
Like, I don't understand why we're taking this integral and what that means in reference to the notation of the.
So in what sense is W an element of D prime? So given that W is locally integrable, any such function can be regarded as a distribution through the following pairing. That W applied to psi is equal to integral of W times psi. Over omega, if you had a domain omega, but here omega is just R. So isn't that the way you consider a locally integral function a distribution? And therefore, by definition, the distributional derivative is equal to the negative of W applied to psi prime. But again, W is locally integrable, and this pairing then is equal to the negative of the integral over R of W and psi prime dx. And so that's where I'm starting here. Yeah. So does that answer the question?
I think so. So if W is in D prime and is L1 loc, then the distribution, that means that W comma phi is that integral.
So if W is L1 loc, it means that you may regard W as a distribution through the following formula, that W applied to psi is equal to W times psi.
Just
integrate.
Okay.
In the same way that if you have A inside Rn, you may regard A as an element of the dual space through the mapping A applied to W equals A dot W. That's the analogy I was trying to draw at the beginning of class. So you could either think of it as a vector, or you could think of it as the function that takes the dot product. Here for the L1 loc function, you could either think of it as an L1 loc function, or you can think of it as a distribution, meaning it takes psi as an input and gives you this as an output. And so since I'm talking about the distributional derivative of W, implicitly, that's the way I must be considering the problem. And once you get to this step, you're going to say like negative infinity to 0 plus 0 to infinity W. psi prime, and then start plugging in your formula for W and do integration by parts. And then you'll see this. And then you'll say, well, this part was the thing that precluded the existence of a weak derivative, meaning it's not going to be true that there is a single function h that I can integrate against to give me the answer because of this. So when you're first getting into this, you might think that h is the weak derivative and therefore the distributional derivative. But it's not, because when you work this out, you get that term. So therefore, W has no weak derivative. And yet W has a distributional derivative precisely because we can exploit the fact that not every distribution has to be integration against a function. So the fact that Dirac delta is a distribution comes in and saves the day and gives us this nice formula. Yeah, Bill.
Just quickly, those two parts of W at slope 1,
Say again.
the slope of those two pieces that you drew, were
Yeah,
they
yeah, yeah.
-1 and 1?
Yeah, I said it in words, but didn't write it down. So when x is less than 0, W is equal to negative x. When x is bigger than 0, W is equal to x plus 1.
Okay, so my follow-up is, wouldn't you get 2 times C of 0, one from each?
I think you get a negative on one side. I mean, we can try to.
I mean, my crude idea is that it's jumping 2, so it would need.
Well, I mean, we're a little bit over time, so I guess I'll just challenge everybody to work out their computation and see. And we'll just
Okay.
reconnect and continue on Monday. Okay, so thank you everybody for your time and attention, and I'll see you Monday, and we'll pick up here. And I've just got like a couple more pages left, and then that'll wrap it up for the semester. And then we'll do your presentations on Wednesday. So thank you everybody, and have a great day.
Okay.